Somewhere beneath the rust-colored dust of Mars, something is happening that does not match the models. Not a theory, not speculation, actual data, pulled from actual instruments, run through artificial intelligence systems built to find patterns no human eye could catch. And what came back did not fit anything scientists had prepared for. A hole that shouldn't be warm at night. Seismic waves that traveled deeper than physics said they could. A mineral that had no business existing where it was found. 3 separate signals, 3 separate instruments, and one uncomfortable question sitting underneath all of them. What exactly is inside this planet? For decades, the story of Mars has been told through its surface. Red dust, dry riverbeds, craters photographed 1,000 times over. A planet we assumed we understood because we could see it. But surfaces lie. They always have. What a planet shows you on top is rarely what it's hiding underneath. And Mars has spent 50 years letting humanity believe it had already given up its secrets. That confidence is now cracking. Because the moment scientists stopped looking only at the surface and started asking AI systems to dig through decades of buried orbital and seismic data, the planet started contradicting itself. Here's where it starts. In early 2025, a paper landed in Geophysical Research Letters that most people never heard about because it didn't come wrapped in a press conference. It came from a quiet cross-check between NASA's InSight lander and the Mars Reconnaissance Orbiter, run through AI-assisted analysis built to link seismic recordings to visible surface changes. InSight had spent years listening to Mars the way a doctor listens to a heartbeat, recording tremors, Mars quakes, faint vibrations moving through rock. Most of that data sat unresolved, patterns without explanations. Then a fresh impact crater was spotted on the surface, and the AI matched it to a seismic signal already sitting in the archive. That match should have been simple confirmation. Instead, it exposed a problem. The seismic waves tied to that impact had traveled far deeper into the Martian interior than existing models of the planet's mantle said was possible. Read that again. Not a new discovery of a crater. A discovery that the inside of Mars is transmitting energy in a way current geophysical models cannot account for. Every model built to describe what Mars is made of, how its layers behave, how heat and shock move through its body, suddenly had a hole in it. Not a metaphorical hole. A literal contradiction between prediction and reality. Think about what that means for a planet we've been mapping for half a century. Mars was supposed to be the solved neighbor, the one place in the solar system we understood almost completely because we'd landed on it, driven across it, drilled into it. But this is a planet that just proved its insides behave differently than the textbooks say, and it took a machine cross-referencing years of unread data to catch it. What else is sitting in that archive? Already recorded, already sent back to Earth, and still unread? That question didn't stay theoretical for long. Because while seismologists were still trying to explain the impossible depth of those waves, a separate AI project was quietly rewriting the map of the Martian subsurface entirely. Not by launching a new probe, but by teaching a machine to see through dust. For years, choosing a landing site on Mars has depended on thermal inertia, a measurement of how fast a surface heats up in sunlight and cools down at night. Solid bedrock holds heat differently than loose dust. That single physical property tells engineers whether a landing site can support the crushing weight of a spacecraft, or whether it will swallow one. The problem was always resolution. Thermal inertia data existed in fragments, gathered site by site, incomplete across most of the planet. Nobody had a global picture. Nobody could say with confidence what was hiding under the dust in the places humans might actually try to land. So researchers trained a statistical model on years of localized thermal data from Gale Crater, where Curiosity has spent over a decade grinding across the surface, and let the AI extrapolate that pattern globally. What it produced were AI-generated thermal maps capable of distinguishing solid bedrock from loose, unstable dust across the entire planet. Not by seeing the ground directly, but by learning the thermal fingerprint of stability itself. This is not a minor engineering upgrade. This is the difference between knowing where a spacecraft can safely stand and guessing. And here's where it gets worse. This mapping wasn't built for Curiosity. It was built because NASA and its partners are already thinking about crewed missions. And a crewed lander cannot afford to guess. Structural integrity of a landing site becomes a non-negotiable safety parameter the moment human lives depend on it. Which means the reason this AI thermal system exists at all is because someone, somewhere, is planning for the day astronauts stand on ground that has never held a footprint before. And they needed to know, in advance, whether that ground would hold. But knowing what's solid and what's loose is only half the picture. Because loose is not the only danger hiding beneath the dust. There is something else down there, something empty. On the western flank of a mountain called Elysium Mons, a volcanic giant that dwarfs anything on Earth, sits a feature that had been sitting in an old catalog for years, mostly ignored, mostly unexplained, an elliptical depression, a shadow that never quite behaved like the shadows around it. In 2025 and into 2026, a team of researchers decided to actually interrogate that feature, pulling together every data set available and layering AI-assisted analysis on top of it, treating the site less like a photograph and more like a crime scene that needed every piece of evidence cross-examined at once. What they found was not a crater. Craters have signatures, ejecta patterns, raised rims, debris fields thrown outward by impact. This had none of that. Instead, high-resolution imagery captured under varying solar angles from the Mars Reconnaissance Orbiter showed an opening with a roof that had partially collapsed, on shadows that persisted no matter the time of day, in a shape consistent with something engineers call a skylight, the kind of hole that forms when the ceiling of an underground tunnel gives way and exposes the void beneath it. On Earth, that means one thing: a lava tube, a hollow corridor carved out by ancient molten rock that drained away and left an empty tunnel behind. But an opening in a photograph could still be explained away as a trick of light and shadow, an illusion of geometry. So they checked the temperature, and this is the detail that turns a curiosity into something closer to alarm. At night, when the Martian surface plunges into brutal cold, ordinary depressions and pits cool rapidly, losing heat into the thin atmosphere with nothing underneath to hold it. But this specific feature didn't cool the same way. Nighttime thermal readings from the Themis instrument aboard Mars Odyssey showed the site retaining warmth, behaving like something with a connected mass beneath it, a signature consistent not with a shallow pit, but with a structure that opens into a larger subsurface space. Sit with that for a second. A location on Mars that is warmer at night than the ground around it has any right to be. Not because of geothermal activity in any dramatic sense, but because it is connected to something underneath that holds heat differently than open air and exposed rock. According to the researchers who compiled this evidence, the combination of morphology, persistent shadow, and thermal retention independently points toward the same conclusion from three unrelated angles. This is very likely a real void beneath the surface of Mars, large enough and structured enough to be classified as a legitimate subsurface access point. And it doesn't stop at temperature. Gamma-ray spectrometer data from orbit showed hydrogen enrichment in the basalt around the site, a signal that, depending on interpretation, can hint at hydrated minerals or trapped volatiles locked into rock that formed from ancient volcanic flow. Mineralogical data pointed toward a volcanic origin for the structure, consistent with a lava tube, and consistent with the kind of environment that could, in theory, have preserved something from Mars's ancient, wetter, warmer past, far more effectively than the radiation-blasted surface ever could. This is not one instrument telling a story. This is 5 independent data sources: imaging, thermal, elevation, gamma-ray, and mineral spectroscopy, converging on the same uncomfortable answer. Now here is the part that should genuinely unsettle anyone paying attention. No rover, no lander, no piece of human hardware has ever entered or imaged the interior of a planetary cave system beyond Earth. Not once, not on the Moon, not on Mars, not anywhere. Every cave candidate identified so far, and there are dozens cataloged across the Martian surface, remains completely unexplored from the inside. We have been looking at Mars for 50 years, and we have never seen what's underneath it. Not really, not directly. We've been reading the surface like a book cover and calling it the whole story. This is not chaos. This is a planet that has been hiding structural evidence of its own interior in plain sight, waiting for someone to build a system smart enough to notice the pattern buried across 4 or 5 different instruments that nobody had cross-referenced before. That's the real story here. Not that Mars suddenly changed, but that AI-assisted analysis is finally catching what human researchers, working dataset by dataset, kept missing for decades. What most people are not seeing is that this is happening simultaneously across multiple research groups, multiple institutions, multiple independent lines of investigation, and they are all converging on the same theme. The surface of Mars was never the real story. The interior was, and that raises a harder question than, is there a cave? Why does it matter this much? Why are researchers explicitly linking this discovery to something called planetary protection, to astrobiological prospects, to resource potential? Because a sealed lava tube on Mars isn't just a geological curiosity. It's potentially the single best protected environment on the entire planet. The surface of Mars is bathed in radiation that would be lethal to unprotected humans over long exposure, stripped of the magnetic field and thick atmosphere that shield Earth's surface. But go underground, into a lava tube, with meters of solid rock overhead, and that radiation exposure changes entirely. Scientists studying planetary caves have already noted that these natural shielding structures may be some of the only places on Mars where biosignatures, chemical evidence of past or even present life, could have survived undisturbed. Think about what that actually means. If life ever existed on Mars, or if any trace of ancient organic chemistry survived the planet's transformation from a warmer, wetter world into the frozen desert it is today, the surface is the worst possible place to look for it. Billions of years of radiation would have scoured away anything delicate. But underground, sealed inside a collapsed volcanic tube, protected from cosmic bombardment, that's where the fragile evidence might still be sitting, untouched, waiting. Which means this Elysium Mons candidate isn't just a structural finding. It's potentially one of the highest priority astrobiology targets identified on Mars in years, and it exists specifically because an AI-assisted multi-sensor analysis pulled together data that had been publicly available and separately ignored. But here's where it gets worse again, because the same discovery that excites astrobiologists terrifies mission planners for an entirely different reason. A hidden void beneath the surface is not just a research opportunity, it is a structural hazard. If AI thermal mapping exists specifically to warn future crewed missions about unstable ground, then a network of undetected lava tubes and collapsed cave systems scattered across candidate landing zones is precisely the kind of hazard that could go unnoticed until it's too late. A skylight collapse strong enough to swallow a rover would be a scientific curiosity. The same kind of instability under a human landing site would be a catastrophe. Every subsurface void identified is simultaneously a discovery and a warning. This is the part most casual coverage of Mars completely skips over. The tension between what makes Mars scientifically extraordinary and what makes it operationally dangerous is the same feature. The caves that could preserve evidence of ancient life are the same caves that could collapse under a spacecraft's landing thrusters. The seismic behavior that reveals a more complex planetary interior than anyone modeled is the same seismic behavior that could shake ground assumed to be stable. Every layer of this discovery cuts two ways. And that duality is exactly why researchers keep using words like non-negotiable and critical when describing why this data had to be mapped before humans ever set foot there. And it isn't just caves and seismic waves. Around the same window of time, researchers working with Curiosity's decade of surface data identified something else strange sitting in Gale Crater, spiderweb-like ridge formations, nicknamed boxwork, crisscrossing the landscape in patterns that don't form randomly. These structures are believed to have formed when mineral-rich water moved through cracks in rock and left behind resistant ridgework after the softer, surrounding material eroded away. That means the ground Curiosity has been rolling across for years is a fossilized record of a much longer, much more complex history of water moving beneath the Martian surface than anyone assumed when the rover first landed. Layer that on top of everything else, and the picture sharpens into something almost uncomfortable in its implications. This is a planet where water once moved underground, long enough to leave structural fingerprints in solid rock. This is a planet with sealed volcanic caverns potentially preserving conditions untouched by billions of years of surface radiation. This is a planet whose interior transmits seismic energy in ways current models cannot fully explain. Individually, each of these is a research paper. Together, they start to look like pieces of the same buried story. A Mars that was far more geologically and possibly biologically active, underground, for far longer than the dry red surface ever let on. Around the same period, scientists studying ancient sulfate deposits on Mars combined laboratory experiments with orbital spectral data and identified what may be an entirely new mineral, one not previously cataloged in any Martian sample or Earth analog. A new mineral means a new chemical pathway, a new set of conditions under which it could have formed, as in one more variable added to a planetary chemistry equation that keeps getting more complicated with every data set that gets reanalyzed. Nobody predicted this mineral. It wasn't on a list of things researchers were hunting for. It surfaced because someone went back through old data with fresh tools and asked a question nobody had thought to ask before. That pattern, old data, new tools, unexpected answers, is the actual through line connecting every single discovery in this story. None of this came from a dramatic new landing or a mission that captured headlines. It came from teams going back through archives that had been sitting untouched, sometimes for years, and applying artificial intelligence systems built to catch correlations across data sets too large and too complex for a human researcher to hold in their head all at once. NASA's own engineers demonstrated this same philosophy directly when Perseverance completed its first fully AI-planned drive across Jezero Crater in December 2025. A vision-capable AI system analyzing the same terrain imagery human planners had always used, but producing a safe route across hazardous ground without a person making the call. That drive matters here for a reason beyond the headline. It proves the same category of AI system now mapping thermal inertia, matching seismic signals to craters, and cross-referencing cave candidates is not experimental anymore. It is operational. It is already driving a rover across Mars right now in real time, making decisions that used to require a room full of trained specialists. Which means the next generation of discovery on this planet is not going to come from bigger telescopes or more expensive landers. It's going to come from smarter analysis of what we already have. And if that's true, the backlog of unexamined Martian data sitting in NASA's own archives may still be hiding more of these moments, waiting for the right algorithm to notice them. A confirmed candidate for a subsurface volcanic cavern on Elysium Mons, verified across 5 independent instruments, sitting completely unexplored, potentially one of the best preserved environments on the entire planet, and simultaneously one of the least understood structural risks facing anyone who tries to build near it, a record of ancient underground water etched permanently into rock, a mineral nobody predicted, and an AI infrastructure now mature enough to have already taken the wheel, literally, on the surface of another world. None of these discoveries arrived with sirens. None of them came with an announcement designed to alarm the public. They surfaced quietly in academic journals, in mission updates, in papers with titles too technical for most people to ever click on. But strip away the technical language, and what's left is a planet that keeps forcing scientists to admit the same uncomfortable thing over and over. We do not know Mars as well as we assumed we did, and every tool sophisticated enough to look closer keeps finding something underneath that the surface never showed us. The real story is not that Mars suddenly became more mysterious. The real story is that we finally built something capable of noticing it always was. And that raises a question nobody has fully answered yet, one that sits underneath every rover mission being planned for the years ahead. If artificial intelligence, cross-referencing data we already had sitting in storage, is capable of surfacing structural contradictions in planetary models, undetected caverns large enough to swallow a landing site, and mineralogy nobody predicted, what happens when the same systems are pointed at the next round of Martian data still being collected right now in real time by instruments already in orbit and already on the ground? Because if the last 2 years are any indication, the surface of Mars was never the difficult part to understand. It was the distraction. The real planet, the one with unexplained seismic behavior, hidden volcanic tunnels, buried water history, and chemistry that keeps producing minerals nobody expected, is the one sitting beneath it. And as more of that hidden layer gets pulled into daylight, the question stops being whether Mars still has secrets left to give up. The question becomes, how many of those secrets are already sitting in NASA's own archives, unread, waiting for a machine smart enough to finally notice them? And what happens the day one of those answers turns out to be bigger than anyone was prepared for?